Welcome back to The Explainer. Today, we are going to unpack an absolutely fascinating, largely forgotten mechanical marvel that powered the past long before everything just plugged into a wall. I mean, if you look around right now, almost every machine, appliance, or tool we use relies on electricity. But there was an entire era of human engineering where a completely different, invisible force was harnessed to do all our heavy lifting. We're talking about the rise and the eventual fall of the water engine. So let's kick things off with a bit of a brain teaser. Think about this for a second. Before widespread electricity, what actually powered London's hoists, heavy cranes, and those massive revolving theater stages? Now, you'd probably guess steam, right? And sure, steam was the superstar of the Industrial Revolution, but the surprising answer for a huge amount of London's heavy, quiet lifting actually lies in an invisible, city-wide network of highly pressurized water. Yes, literally just water. All right, let's dive into Section 1, Meet the Water Engine. Picture this. If you walked right up to a positive displacement water engine back in the 19th century, you would probably mistake it for a standard steam engine. It's got the heavy metal pistons, the intricate valves, all the mechanical arms, the whole shebang. But here's the catch. Instead of a boiler furiously burning coal to create expanding steam, this engine was driven entirely by water pressure. This water could come from a high-elevation reservoir, standard city water mains, or a specialized high-pressure supply line. It was just a totally brilliant repurposing of existing mechanical engineering. Now, the real secret sauce here comes down to a really cool quirk of physics. See, with a steam engine, you're working with a gas. Steam is highly compressible. It expands, it gives, it creates the spongy elastic force that bounces pistons back and forth. But a water engine uses a liquid, and water, in practical engineering terms, is virtually incompressible. That single difference in physics makes the water engine a completely different, and honestly, a much more stubborn beast to tame. Which brings us nicely to Section 2, the engineering challenge. Because when you try to harness a force that absolutely refuses to compress, you run into some serious, even dangerous hurdles. We really have to emphasize this scientific fact. Water is virtually incompressible. Imagine water rushing through a thick pipe at high speed, driving a heavy metal piston. With steam, if you suddenly close a valve, the steam just compresses and acts like a cushion. No big deal. But with water, if you shut a valve too quickly on a rushing stream of pressurized water, that kinetic energy has literally nowhere to go. It creates an immense destructive force. It's like what plumbers call water hammer, but on a massive industrial scale. If engineers weren't careful, the entire pipework of the engine would just violently explode. So how did they stop everything from blowing sky high? Well, ingenious 19th century engineers came up with some brilliant mechanical workarounds. First, no snappy, fast-acting valves allowed. They had to specifically design valves that close slowly and deliberately to ease the water to a stop. To get the timing perfect, some engines even had a tiny secondary engine attached, whose only job in the world was to safely operate the main engine's valves. And finally, they built in air chambers. Since water won't compress, they trapped pockets of air inside the engine. When the water pressure spiked, that internal air would compress instead, acting as a built-in shock absorber. Just an incredible, delicate dance of high-pressure engineering. Let's move on to Section 3, powering 19th century London. Okay, so how did this actually look in the real world? Well, a standard municipal water main in 19th century London gave you about 30 to 40 pounds per square inch, or PSI. That's decent. It gets water to your upstairs bathroom, and you could definitely hook up a tiny water motor to your kitchen sink to run something light, like a sewing machine. But 30 to 40 PSI is absolutely not going to run heavy industry. For that, London needed a whole lot more juice. Enter the London Hydraulic Power Company. These guys built a massive, totally specialized network of pipes right beneath the city streets, dedicated solely to delivering high-pressure water to industries. And they cranked the pressure all the way up to an astonishing 800 psi. I mean, that is a gigantic jump in power. Suddenly, you've got this subterranean grid capable of running heavy industrial-grade machinery, powered by nothing but pressurized water. Now, you might be wondering, once electricity was invented, didn't these water engines just become obsolete overnight? Actually, no. They survived well into the early electric era for a few very specific reasons. Unlike early sparking electric motors or clunky steam engines, water engines were incredibly quiet, they were super reliable, very compact, and actually quite cheap to run if you were already hooked up to the network. But here was the real game changer: safety. Imagine you're in a dark, flooded coal mine. An early electric pump down there is a massive electrocution hazard. But a water engine? It operates perfectly safely, even when completely submerged underwater. For mine pumps, they were an absolute lifesaver. And thanks to that 800 psi network, the uses were just everywhere. Railway companies used this massive hydraulic power to literally spin multi-ton trains around on turntables. It powered heavy cranes and hoists all along the London docks. It even crossed over into the arts. If you caught a show at the London Palladium or the Coliseum Theatre, those gigantic revolving stages were being turned smoothly and silently by water engines beneath the floorboards. They're even used to supply the enormous steady airflow needed to play massive pipe organs in grand halls. Let's scale things up in Section 4, Giants of the Mimes. So we've seen the city theaters, but let's zoom out to the macro-industrial level. Meet the absolute behemoth of this technology, the water column engine, or if you want to practice your German, the Wassersäulenmaschine. This was the largest possible design of a directly acting water engine. We're talking colossal machines running on a single giant axle with differently sized pistons. They didn't just spin a wheel, they acted more like massive hydraulic rams. By taking a huge column of falling water on one side, they generated enough raw power to pump millions of gallons of heavy saltwater brine, or to pump out flooded deep shaft mines. It's really cool to trace the historical journey of all this. It starts a bit mysteriously around 1600, when Robert Flood described an early water pump after a trip to Germany. By the mid-18th century, these things are everywhere in Central European mining towns. In 1810, an engineer named Reichenbach builds massive water column engines specifically to pump brine from Berchtesgaden to Reichenhall. But look what happens next. As we roll into the 20th century, the technology drastically shrinks. In 1914, the company Miele introduces tap-powered wooden washing machines for your house. And believe it or not, domestic water engines like that hung around until the 1960s before finally fading out completely. Which brings us perfectly to Section 5, tap-powered washing machines. So we're transitioning from mountain-moving brine pumps to, well, doing the family laundry. How did this work in a regular kitchen? With a 1914 Miele, you would literally hook a hose from the wooden tub directly to your household tap. You turn the tap on, and that normal mains pressure drives two internal pistons back and forth. Those pistons then mechanically rotate a star handle built right into the lid, creating this perfect, steady to and fro motion that swished your clothes through the soap suds, or the log as it was called in German. The water pressure from your tap was literally doing all the exhausting back-breaking scrubbing for you. I know exactly what you're thinking. Doesn't that waste an unbelievable amount of fresh drinking water just to spin a wooden tub? Well, as one of our sources points out, plenty of used water was often available and was very cheap. See, in thrifty rural households, the sheer volume of water wasn't really a problem. Because it was running through a completely sealed engine, the water came out just as clean as it went in. The runoff was simply captured in a bucket or trough and immediately repurposed for watering the garden, washing the floors, or other farm chores. Literally, nothing went to waste. But okay, let's be real for a second. It wasn't a totally flawless system. There were some highly relatable drawbacks. The biggest one, water pressure consistency. If you tried to do laundry right before or after work, which is exactly when the rest of your town was opening their taps, the water pressure would just plummet, and your washing machine would slowly grind to a halt. Plus, they were completely useless during hard winters if your pipes froze solid. Because of all this, every single one of these machines came with a manual backup. If the tap failed, you had to disconnect the engine, grab the handle, and use your own muscle power to finish the wash. It is just wild to think about, isn't it? A foundational technology that rotated massive theater stages in London and washed clothes in rural Europe for decades simply vanished when modern electric motors got cheap and reliable enough. It really makes you wonder, what piece of modern infrastructure that we completely rely on today, something as invisible and normal to us as high-pressure water networks were to the 19th century, might just vanish into total obscurity over the next 100 years? It's definitely something to chew on. Thank you so much for joining me on this explainer of the water engine, and as always, keep on learning.